our tube banks. So, as we discussed in the last class, that tube banks are usually found in heat exchangers, and we can definitely see them at the back of our fridge. The coils, the black coils, which are placed behind our fridge or refrigerator, they are basically the condenser for the fridge, which removes the heat to the atmosphere, and that heat is absorbed in from inside the fridge cabin. Okay, so then we discussed in the last class that we analyze this problem as a unit problem. So that it means that we determine the Nusselt number for the whole tube bank rather than analyzing an individual tube. So it means that if this is a tube bank, then for this we are going to analyze this tube bank. This is basically a tube bank. So we analyze this as a unit. So it means that we need to write Nusselt number correlations for this. So for that we can use again that CREM and Prandtl number, and then there is another. Uh, okay, so we would come to that the exact form of the correlation in the end of this lecture. So before going into that, we discussed about two arrangements. If you remember, one was inline arrangement. So it was basically the arrangement in which we have got a number of, the flow direction is x, and then we can easily see that there is no hindrance of flow when the flow passes through one set of tubes. Then it goes straight towards second set and then the third set. So if we define the directions here, so we have got longitudinal direction, which is the flow direction. So let me write it here. This direction is longitudinal direction, and the distance between these consecutive number of tubes, that is represented by SL. And then if we go here, this direction, this is transverse direction in the y direction, and then for this we have got this ST, right? So this is basically they are longitudinal pitch and transverse pitch. And then if we want to determine the diagonal pitch, we can easily determine by using the Pythagoras theorem, which is SD. If it is SD, that is equal to, in this case it is equal to SL square plus ST square. And if this was only for the inline arrangement. For the staggered grade, we have got a tube in between the in the vertical direction. We have got a hindrance, so it means that if a flow comes here, it has got two options: either it can go this way or this way. So it is kind of flow over a pipe or cylinder in this case. So uh, for this, if we want to determine SD, that would be equal to SL square plus ST divided by 2. So SD definition would be a little bit different for the stagger grid. So in the stagger grid, the tubes in from one row to the other row, they are kind of staggered. So it means that they are in the path of the flow. So it means that the flow has to split in two directions here, and then it would join afterwards in the here, and then again we would have another tube here, and then it would go on like this. Okay, so this thing I think we discussed. So it was just a repetition. So this is SD, this is ST, and this is SL. So longitudinal pitch, transverse pitch, and diagonal pitch. So anything which is not clear up till now, any query from the last lecture, anything which was not clear, so please let me know. No, otherwise we can start the discussion about tube banks in detail in this lecture. Okay, so it seems that everything is good. So as I discussed that for the tube bank case, we also need to determine Nusselt number correlations. Now, in order to determine Nusselt number correlation, once we get the Nusselt number correlation, then we can use this formula Hp upon Ko weight and to get the value of H. Okay. So this is our line of action. So it is the same thing as we did for the uh, for the cases of flow over flat plate and flow over sphere and cylinder. But the question here is that because you know that we defined the Reynolds number in cases for the flow over flat plate and Reynolds number. So in this case, we also define Reynolds number. But uh, if I show a diagram, and let me draw inline arrangement here again, just for the sake of explanation. So first of all, we talk about inline arrangement. So here we have got two tubes. So this distance is st. Okay, if the flow is coming from here and approach velocity is, let's suppose we have got u infinity. Now, can anyone tell me that where would be the maximum velocity? At which cross section we would have the maximum velocity in x? Because if you remember your thermodynamics course, whenever we have got the least cross section, the place where we have got the least cross section, so at that point we would have the maximum velocity. So that is this place. Here, the distance uh, between these two is st minus d, right? So it means that if it is u infinity, it is for the st1. So here it it would be v max, right? Because we have got the least cross section here for the flow. So it means the from the conservation of mass principle, the velocity would be maximum at this location where we have got the this least cross section. So for flow over tube banks, we define Reynolds number as rho u max into diameter divided by mu. Right. So what is diameter? Diameter is this diameter of individual tube. Right. So how to calculate U max for inline arrangement? It is quite simple. We can apply if you remember that mass flow rate formula was equal to rho into rho AV. You remember this formula. So if we apply conservation of mass between this location and the location of the maximum velocity, we can always determine the Vmax in terms of u infinity. So I think we can do it. So if we first of all, if we determine the mass flow relation here at the place of u infinity, we can write rho rho into now u infinity into st into L. L, what is L? Because in the third direction, the length of the tube is L. If I go back to show you that what is that capital L, let me go back to the original diagram, the first diagram here for the refrigerator. So if you see that from if we are looking from the front, we would be looking at the cross section of the pipe. So this is sorry, this is the length of the pipe, right? Because it goes from here to here and then it comes back and then so it means that this is the length. This is length, right? So flow is coming from the front. So from the this plane, if flow is going like this from the bottom or top plate, so we can have this length of the plate. So that would determine the mass flow rate. So I hope that this thing is clear that what is this capital L, that is the length of the cylinder in the that direction. So that would be equal to rho into V max Okay. Can you anyone confirm that you can hear me now? Javed?
Yes, sir. Yes, sir.
जी सर.
How long that there was internet connection problem?
सर अभी 2 सेकंड, दो
Okay.
सेकंड पहले.
Okay, ji. Thank you very much. So, are you understanding that what we are discussing at the moment? We have applied the conservation of mass principle between these two locations. If I say it A location and B location, so at A location, there if we determine the mass flow rate, that would be equal to rho into u infinity, which is the velocity here. St is the distance between the transverse pitch into length. Length is the length of the pipe in the that direction. So that is equal to if we apply the conservation
सर
of mass.
स्क्रीन शेयर कर दें.
Okay, sorry. Let me do that again. I hope that this is visible now. The screen is visible.
Yes, sir.
Okay. So we were discussing about. Let me tell you again, and just for the convenience, we have applied the conservation of mass at location A and at location B. So for the location A, the mass flow rate would be equal to rho into, because we are taking it incompressible flow. So let me write here for the incompressible flow, the density would be constant. Rho would be the same at location A and B, because for the incompressible flow, the density doesn't change. So in that case, we would have rho into u infinity into st. St is the this distance, and then L is the capital L is the length of the tube in the into the board, which is the third direction, and then at mass flow rate at point B would be equal to rho Vmax. Vmax is the maximum velocity that is due to the nozzle effect, that where we have got the least cross section for the flow. there we would have the maximum velocity. As for the nozzle case, if we remember that maximum velocity was at the throat of the nozzle, and then we can apply the convergent part as well for that to have hypersonic flow here. So supersonic flow. So the here the nozzle is choked, so it means that we would have kind of sonic velocity here. So that is the same effect. So that is the throat of the kind of the nozzle. So we would have maximum velocity, and the distance here, that is st minus d into length, because the length of the tube is the same at the both direction. So here, if we do the simplification and determine Vmax, so we can kind of cancel out this row, and then we can write Vmax is equal to U infinity into St, because this length would also be cancelled out on both sides. So here it would be St minus T. So it means that we have got Vmax relation for the inline arrangement. So this is applicable for inline arrangement. Why we need Vmax? I would repeat again that Vmax is needed for the determination of Fresnel number, because here it would be, let me do it, stick with the same terminology, so it should be Vmax. Okay, now when it comes towards the second arrangement, which is staggered arrangement, we need to determine the Vmax for the staggered arrangement as well. Right. So let me draw that here, just for the convenience of the for the clarity of the class. So now if I draw it here, right, you can assume that the diameter of all these tubes is the same. So it is not as per the scale, but you can assume, always assume. So in this case, we have got this is S L, this is, as before it was S T. This place would have St minus D. What is D here? D is the diameter of this uh, tube. So d by 2 would be the distance from here to here, and d by 2 would be the distance from this point to this. So that's why we have subtracted st minus d. Okay, now for the staggered arrangement, there are two possibilities of the Vmax. One is the same thing, because now one place is this where the Vmax can happen, and then the second place is this. Okay, let me, at this point, if we join this with this, so we would have this distance would be SD minus D. What is SD here? I should write it again. SD here is SL squared plus ST divided by 2. Right. So, and here it would be also SD by D. So it means that if there is possibility one, we can write it possibility one. If 2 into SD minus D is sorry, if it is bigger than ST minus D, right? So it means that ST minus D is small. So it means that Vmax, the location of Vmax would be here, still here, because we have got the smaller where we have got the smallest cross section. There we would have the maximum velocity. So it means that Vmax would have the same formula as we determined for the case of inline arrangement. So that was equal to St upon St minus D into U infinity. Right. So if we have got this possibility, okay, when we have got this thing. Now we consider the possibility number two. So for that, let me plan it a little bit. Now the possibility two is when we have got if 2 into SD minus D is smaller than ST minus D. In this case, it means that the location of Umax would be at this point here. This would be Vmax now, because two times this, because the flow is split into two directions here. Half would go this way, half this would go this way. So even if this two times SD minus D is bigger than this ST minus is smaller than ST minus D, then we would have, if we apply the conservation of mass, then we can write a little bit. So here we can write, then again, as we did, rho into U infinity at point 1, it would be equal to St into L, and on the second hand, on the second, if we apply conservation of mass here, it would be rho into U max into 2 times S, S D minus D
सर
into, yes,
सर इधर आपने लिखा है कि 2 इंटू एस टी माइनस टी इज मोर देन एस टी माइनस टी, तो
yes.
लेकिन हम उसको 2 टाइम्स हम उसको कंसिडर कर रहे हैं, बट फ्लो तो सिर्फ एक से ही गुजरेगा, तो एस टी माइनस टी इज ऑब्वियसली लेस देन एस टी माइनस टी नहीं। लेकिन अगर हम 2 टाइम्स कर रहे हैं तो फिर वो ग्रेटर है, लेकिन अगर हम सिंगल कंसिडर करें तो वो स्मॉलर होगा।
Okay, ji. Thank you very much for asking this question, because it is not very easy to comprehend. So thank you for the question. Let's suppose, Minahil, we have got the flow coming from here. Okay? Oh, sorry. If the flow is coming from here, right? Now tell me, when it approaches somewhere here, there is a cylinder here, right? There is a tube here. Minahil, what are the options for the flow? Either it would go in this direction, half of the flow would go in this direction, and half of the flow would go in this direction. Is that right, Minahil?
यस सर।
Right. So tell me then whether we would use 2 times SD minus D or single SD minus D in the formula.
2 टाइम्स।
2 times. So it means that 2 times SD minus D is bigger than ST minus D. So it means then because the cross sectional area here is more, then it means that the maximum velocity location would be the same as it was for the inline arrangement. Is that clear?
यस सर।
Okay, but there can be a possibility when we have got, because from this figure, if we see the figure, we can readily see that SD minus 2 times SD minus D would always be bigger than ST minus D. Okay, that is clear from this figure. But if we arrange it, if we kind of have an arrangement when we have got this very close, then what will happen? If it is very close and they are, it means that SL is very small and ST is very bigger. Then it means that in the transverse direction they are quite apart, but in the longitudinal direction they are quite close. Then in that case, there may be a scenario when this 2 times SD minus D would even be smaller than this ST minus D. In that case, because now 2 times SD minus D is smaller than ST minus D, so from the conservation of mass principle, the maximum velocity would be at the location of this diagonal pitch. Minahil, is that clear?
Yes, sir.
Okay, so that would be only the case when SL is very small and ST is very bigger. At the moment, because ST and SL they are almost equal, so that's why SD 2 times ST minus D would always be bigger than ST minus D, right? But if we move it in this direction, it means that in the flow direction, if we decrease the distance, and in the transverse direction, if we increase the distance, then 2 times ST minus D can become smaller than ST minus D. Okay. So now going back there, possibility 2. So if we apply this conservation of mass, let us do the simplification. Rho cancel out with rho. I haven't completed this formula here, so ST into L. So if we do the cancellation of L, then from here we can write Vmax. It should be Vmax, right? Because in the book they have used Vmax, so I am using the same notation. Vmax is equal to St divided by 2 times St minus T into U infinity. So this relation for the Vmax is applicable in case of staggered arrangement when we have got St minus S 2 times St minus T is smaller than St minus E, and I have told you that would be only possible when SL is far greater than, sorry, ST is far greater than SL. It means that in the longitudinal flow direction the distance is very small, but in the transverse direction the distance between the two tubes is very large. Right. So now we have discussed this thing, and now once we get the Reynolds number Vmax, then let me write the relation for the Reynolds number. That for this case it would be rho Vmax into diameter divided by mu, and D is the, here D is the external or external diameter. Okay, because the tube can be thick walled, so we can write it external diameter of the tube. Okay. So now let us move back to the slides, and because we have discussed everything on the whiteboard, so let me quickly go through the slides. So as we discussed that it is the situation where the flow crosses over the tube. So it is not in the over the length of the tube, but it is going across the tube. So they are quite frequently, these tube banks are quite frequently present in all the heat exchangers like condenser, evaporator of power plant, boilers, refrigerators, air conditioning. So in such equipment, one fluid moves through the tubes and the other fluid moves over the tubes. So we are considering the flow over the tube at the moment. From the next week, we would be considering the flow, the force convection of the fluid which is passing inside the tube. So that is the force convection inside the tubes. That is the next step. So in the heat exchanger, that involves a tube bank. Tubes are usually placed in a shell, so we call it shell and tube heat exchanger. When the fluid is a liquid passing through the tube, and the gas usually flows inside the space between these tubes. So that is the flow we are considering at the moment. When analyzing heat transfer, we usually consider it as a bundle, as one entity, rather than considering one tube at a time. So the tube arrangement, they are inline or staggered. So I have shown that here. If you see here, for if the flow direction in the y direction here, you can easily see that the flow, if the flow is from the bottom to the top, so if the flow is entering here, it can easily go straight towards the second row, then the third row, there is no hindrance. But for this case, if you see that we have if the flow enters a row of the tube from the bottom, it has got immediately another tube here in front of it. So the flow either goes this way or this way. Now you can see that staggered arrangement now, because this SL, which is the distance between two tubes in the flow direction, is very less here. You can easily see that 2 times SD minus D can be less than this ST minus D here, right? Because the flow direction is y direction, right? So because in this case, SL is very small as compared to ST, right, which is this in this case, because the flow direction is y. So I hope that this point is clear to you all, that when that possibility too can happen here for the staggered arrangement. So right, so this we discussed, and then we discussed about that if we want to calculate the area for the flow here, A1 is ST into L, AT is ST minus D into L, and AD is SD minus D into L, which we have already discussed. Outer tube diameter is taken as characteristic length, and the arrangement of the tubes in the tubes are characterized by the these three types of pitch which we discussed, and the diagonal pitch for the inline arrangement, that is SL square plus ST square, and for the staggered it is ST divided by 2. Why is that? Because here if you see that for the staggered arrangement, the next tube is at the half distance, so it means that it would be ST minus here if we calculate the vertical distance, that would be ST divided by 2, right? But here for the inline arrangement, if we determine the vertical distance between these two tubes, that is ST. So for the SD calculation, that is different for the staggered and for the inline arrangement a little bit. Right. And then as the fluid enters the tube bank, the flow area decreases. As I have explained that here the flow area is ST, but when it comes here, it decreases to ST minus D. And then we determine the Reynolds number depending upon V max rather than U infinity, which is the approach velocity which we use for the flow over a single cylinder or sphere, or for the case of flow over flat plate. So for this case, the maximum velocity is determined from the conservation of mass requirement for the incompressible flow. So for the incompressible flow, we know m dot at this location would be equal to m dot at this location. So we applied this conservation of mass here. There should be st into L and st minus d into L. So L would be cancelled out, rho would also be cancelled out. So it comes out to be st upon st minus d. So that is the case which we discussed for the inline arrangement. And then secondly, we discussed the two possibilities for the maximum velocity calculation for the staggered grade. So that depends upon the location of the maximum velocity. So if 2 times sd minus d is bigger than st minus d, then it means that the maximum velocity still occurs at this location, which is st minus d. So the same relation for the Vmax, which is st divided by st minus d. But if SL is very small and ST is very big, then there can be a situation as it was evident in the figure shown here. Because here the SL is this direction and ST is this. Because the flow direction is this, so SL is this. So SL is very small and ST is very big. So for this situation, we can have 2 times SD minus E smaller than ST minus E. So in that case, we determine that ST is equal to Vmax is ST divided by 2 into ST minus T V infinity. So once we get Vmax, we get Reynolds number. So Reynolds number is calculated Vmax into diameter divided by kinematic viscosity, which is equal to mu upon rho. So rho comes here and mu comes here. So once we get the Reynolds number, we can get the Nusselt number from the same correlation C into power law RE D. M is the constant which needs to be determined by the experiment. Prandtl number N is the coefficient of Prandtl number, and then Prandtl number into Prandtl number S. So this Prandtl number, it is determined at the mean velocity, which is the average of inlet temperature and outlet temperature for the fluid, and then PRS, that is calculated at the surface temperature, right? And then there is a table for the Nusselt number calculation for different ranges. We can see that the coefficient of C here is 0.9, 0.52, 0.27, 0.03, and here it comes from 1.04 if Sagre arrangement. So we can have all these relations, we can use them. And then M value is kind of if you see that M value is 0.4 here, 0.5, 0.63, 0.8, and then N value is 0.36. Here it is 0.4. So we can use the relation as per the Reynolds number. What is the Reynolds number? And then we can use the corresponding relation. Okay. So, but here it is, if you look at the caption of this, Nusselt number correlation for cross flow over tube banks for N greater than 16. So N is the number of tubes in the longitudinal direction. Okay, longitudinal direction means the flow direction. It means that these relations are only applicable if we have got 16 number of tubes. If we have got the number of tubes in the flow direction less than 16, so if it is equal to 16 or more than 16, then we can apply these relations. Okay, but if the number of tubes is less than 16, then it means that we need to correct that Nusselt number value. That, because why we need that correction? Because from the experiment they have found out that if the number of flows in the flow direction is less than 16, then the Nusselt number value which comes out from the number of tubes is more than 6. So that correction factor which needs to be determined, that is given in this table. Now you can see for the tube bank with number of tube rows and L. L means that the
Excuse me,
longitude.
sir.
Yes.
सर आपकी स्लाइड शो नहीं हो रही सर.
Is this the case with Atif only, or is this the case with everyone?
Sir, everyone.
Okay. So when did this occur? Because it was showing.
सर बस
Sir,
5-10
just
सेकंड पहले.
Okay. Thank you very much for telling me. So I would share it again. So let me share it again. Can you see the screen now?
नहीं सर।
No, sir.
सर ब्लैक स्क्रीन शो होती है, स्लाइड में शो हो रही है।
Okay, ji. So what I would do that I would leave this meeting and I would rejoin it. So hopefully it would resolve the issue. So just hang with me for maybe couple of seconds. So I would be joining back. Okay, I am going to share the screen now again. Hopefully we can see it. Can we see it now?
यस
Yes,
सर।
sir.
Okay, thank you.
जी सर।
Good. So I was discussing the correction factor here. So let me kind of revise it. Maybe it would be good for your knowledge again. So all these relations which I have shown you, that is only applicable when we have got the number of rows. Here if you go here, it is written first row, second row, third row. So those relations are only applicable, Nusselt number correlation, when the number of rows in the flow direction, they are equal to 16 or more than 16. Then we can use these relations. If the number of rows in the flow direction is less than 16, then we need to apply a correction. So that correction factor is F. So because the people who have done these experiments, they have found out that the Nusselt if the number of rows are less than 16, then the actual Nusselt number that should be that we should be getting, that should be less than the relation which they have derived for these relations. So that's why they have put those corrections. So if we have got only one row, then the Nusselt number which we have here, NUD, that is the Nusselt number which we get from these relations. So if the number of row is only one, then we need to multiply it with 0.70 for the inline arrangement or 0.64 for the staggered arrangement, right? If the number of rows are 2, then we need to multiply it with 0.80. Then, okay, it has given the values for the number of rows for 1, 2, 3, 4, 5, 7, 10, and 13. Okay, if the number of rows are 6, what we need to do? Anyone?
The
सर 5 और
interpolation.
7 का मीन।
बिल्कुल जी, जैसे हमने in thermodynamics, we if we can say that if we haven't learned anything, but if we one thing we can say for sure, that we have learned that how to do the interpolation bit, because that was the thing we did in the steam table to calculate the properties, I think. So for this we can at if we want to determine at 6, we don't need to do interpolation, we can take the average between these two. But if we want to determine at 8 or 9, then of course we want to have that interpolation, right? So this is the correction factor which we need to apply if the number of rows are less than 16, right? So okay, now let me take you back to whiteboard. Okay, let me pan it a little bit. So okay, let's suppose we have got a tube bank here. So just for, because I want to explain something which is a little bit, I would have maybe 3 rows, right? So let's suppose here the surface temperature of this tube is like 100 degrees. All the tubes are at 100 degrees. So we call it TS. Air which is coming from here, the fluid which is coming here, that is at T infinity, or we call it Ti, because we call it inlet temperature. Here after the tube exit, it would have Te. When these tube bank would be ended, after that the temperature of the fluid which is going across this tube bank, that temperature would be Ti. Okay, so tell me, if it is 10 degrees, so at first row, what is the temperature difference which is available for the heat transfer? Anyone?
90 degree.
90,
9.
90 degree, right? So it means that at the first row we would have the maximum temperature, maximum heat transfer, because Ts minus Ti would be 90 degree. Is that right? Is it understood to everyone? I hope that this point is clear. Now,
Yes, sir.
because there would be some kind of heat transfer from this, it means that the temperature of the air would rise a little bit. So, if I say that at this point it becomes 15 degree, okay, that is kind of assumption that because when this air becomes in contact with the outer surface of this first tube, so because of the maximum temperature difference, which was 19, so it gains 5 degree, so the air temperature now becomes 15 degree. Okay, maybe 20 degree. Okay, not 15, maybe I call it 20 degree here. Right. Now the temperature difference between the second row between Ts and this, it is 80 degree. It means that now the heat transfer would decrease, and then maybe here it would be 25, and then 25, and then here the temperature difference would be even less, it would be 75 degrees. Are you getting this, everyone?
Ji, sir.
Okay, so let me draw it here on a diagram. This is temperature. This was Ts, which is 100 degree. This was Ti, which was I think 10 degree. Okay, now you can see that in first, in this the temperature rise is 10 degree here. ठीक है, temperature rise delta T, but here it is 5 degree. ठीक है, तो इसका क्या मतलब है? What does it mean? Oh, sorry. It means that here we would have exponential increase, rapid increase in the first bit, and as we go along, then it would be kind of going like this. So it means because in the first few layers we have got the maximum temperature difference available, so it means that the majority of the heat transfer would be happening in first maybe 6, 7, 8, 9, 10 rows. So it means that adding more than 60 rows, maybe 20 rows, it would be not very beneficial, because the area under the curve which is going to be helpful in that heat transfer, that is this area. ठीक है, ये जो ग्रीन एरिया मैंने आपको बताया, और अगर आप देखें this green area is maximum occurring in this, in the initial layer. So if we apply the standard heat transfer formula, the standard formula which we can write it, that the Newton law of cooling, that is HAS into TS minus, actually it was T infinity, right? Now there is no T infinity. ठीक है? Why there is no T infinity? Because temperature is Ti here and Te is here. ठीक है? क्योंकि at each row the temperature, this T infinity, it was 10 degree in the first row, it was 20 degree here, it was 25 here. So it means that this T infinity is changing along the rows. So it means that the very crude way of determining this T infinity, that is, we can do it Ti plus Te divided by 2, we can take a mean of this. Okay? But that we can only do if this temperature rise was somewhat, if I draw it rainbow pen, let me try this. If this was something like this, if this was linear increase, then I could have used this T infinity. Now if you see that if we use this T infinity formula here, then the area under the curve would be very high. Are you getting this? Anyone? Because then we are considering this additional area. When we are considering this additional area, then it means that whatever Q value we would be getting by using this T infinity formula or T mean formula, then it means that it would give us very high value of heat transfer, which is not practically happening, because in the practical actual case, majority of the heat transfer is happening in the first few due to the exponential increase of this temperature. Do you understand this point? Anyone?
Yes, sir.
Okay. If anyone who has got any confusion regarding this, you should ask. ठीक है?
सर नहीं नहीं आया समझ सर.
जी आतिफ. ओके. ये जो फर्स्ट लेयर मैंने ड्रॉ की, ये वाली जो एक्सपोनेंशियल इंक्रीज वाली बात थी, वो आपको समझ आ गई थी आतिफ?
यस सर.
सो इट मीन एक्सपोनेंशियल इंक्रीज में जो हमारा जो एरिया अंडर द कर्व था, वो ये ग्रीन वाले था. ठीक है? ये आपको ये क्लियर हो गया?
यस सर.
अच्छा जी. अब अगर हम आए न्यूटन लॉ ऑफ हीट कूलिंग पे, वहां पे अगर आपको याद हो, फार्मूला होता है ना HAS TS माइनस T इन्फिनिटी. नो
यस सर.
T इन्फिनिटी हमारे TS की वैल्यू तो चले 100 है. नो व्हाट अबाउट T इन्फिनिटी? T इन्फिनिटी इज द एयर टेम्परेचर. ठीक है ना? अब एयर टेम्परेचर शुरू में 10 था, आस्ता आस्ता वो इंक्रीज हो रहा है. इज दैट राइट आतिफ?
यस सर.
So it means that for the T infinity we need to take some average value or anything. So the first way of doing that is that we measure the temperature at the inlet of the air and at the outlet when it exits the tube bank, and then take the average. That would be T infinity. ठीक है ना? One way of doing things. ठीक है?
यस सर.
ठीक है. लेकिन अगर वो हम कर रहे होते हैं तो वो physically, यानी कि on physically what we are doing, then we are saying that T infinity is the mean of T inlet and T exit. So that is this curve. We are drawing the linear. We are taking the average. So we are drawing the. So in that case, our T infinity is somewhere here. ठीक है? Because that is the average of Ti plus T. T is the temperature here. Atif, are you with me?
यस सर.
Now you can see that if we use this linear line, the area under the curve increases very much. Do you understand this?
यस सर.
तो इसका मतलब ये है कि ये जो लीनियर एजम्पशन लेके अगर हम करते, तो जो हमारे पास Q की वैल्यू आएगी, क्योंकि अब एरिया अंडर द कर्व ज्यादा है, तो हमारे पास जो Q की वैल्यू आएगी, that would be Q calculated from here would be very very higher than Q actual. Q actual क्या है, जो कि ये जो ग्रीन एरिया अंडर द कर्व है, ग्रीन एरिया अंडर द कर्व से हमें Q actual मिलेगा, ठीक है. तो Q actual is very less, but Q calculated by this relation is very coming out to be very large because we are using this thing. Atif, does it make sense now?
Yes, sir.
Okay, so what can we do? That we can use this for this we can use logarithmic formula for accounting for this exponential increase. So let me pen it a little bit. So we can write it. Let me write it in Q is equal to HAS into delta T logarithmic. Okay, so what is delta T logarithmic? That is equal to now that is I am going to write a few formulas. Don't worry about that. We are going to derive it in the next chapter. Uh, at the moment, you just take it as it is. We are going to derive this formula in the force convection through internal flows. Right. So this is the formula for this. So it is quite easy to remember if I write it here. Delta Te minus delta Ti divided by log of delta Te divided by delta Ti. Okay, delta Te किसके इक्वल है, Ts minus T, delta Ti किसके इक्वल है, Ts minus Ti. अच्छा जी, so we would go towards the derivation of this maybe in next week's lecture, but at the moment, so at some for some cases we don't know the value of T. So if we want to determine that, there is another formula for that. Let me write it here. That T can be written as Ts minus Ti into exponent minus HAS upon m dot Cp. This HAS upon m dot Cp, this is called NTU, number of transfer units. We are going to discuss this thing in detail in the internal force conversion. So don't worry about this. This formula, T formula, would be also be derived there. So you need to just take it as it is at the moment, and we would do that from where these formulas came. So in order to have a realistic value of Q dot, we use delta T logarithmic. So that was instead of using that mean value, which we shown here, that if we employ the mean value, which is Ti plus Te upon 2, then the area under the curve would be very high. So Q calculated would be very high as compared to the actual heat transfer happening. So our design calculation would be incorrect. So in order to be our calculations to be realistic, we need to use delta T logarithmic. So in that case, we would have a realistic result. Okay, so uh, that is I have written these two formulas, but I have explained you on the whiteboard that why we need these two formulas. That use of mean temperature for determination of Newton law of heat cooling. If we do that, then it would give us very high value of that heat transfer. So in order to have actual value, we use logarithmic temperature difference. Okay जी, so AS is N by DL
सर
and yes, Charis.
सर अगर हम हर स्टेप में जो हर ट्यूब के बाद चेंज हो रहा है एयर का प्रेशर, उसके हिसाब से हम क्यू निकालें और बाद में सबको ऐड कर दें तो
बिल्कुल, you can do that, but if you have got 100 number of rows, then good luck with that. And why you need to do that? It is doing your Gauss Seidel iteration on paper. ठीक है, आप जैसे कहते हैं ना कि गॉस सीडल आइटरेशंस करते हैं, न्यूटन रेफरेंस मेथड होता है. व्हाई वी यूज कंप्यूटर्स फॉर द एनालिसिस? आतिफ, इज दिस आतिफ और शारिफ?
Yes, sir.
ठीक है.
Atif, sir.
So why we need to do that kind of very cumbersome work when we can do this on paper easily? ठीक है, you can do that, but we don't need to do that if we can have this logarithmic temperature difference, which is going to give us realistic results. ठीक है.
Okay, sir.
Because if we employ your technique, of course we can do that, but it would take a very long time. ठीक है, and time is the money. ठीक है, in actual situations where we need to come up with any design conditions, and we have got very tough deadlines which we need to meet. ठीक है. So usually we do this kind of analysis by using software like ANSYS software, but for the rough calculations, you can always employ these techniques, those correlations, which I have shown you. Okay, so this was about the heat transfer, but because Sinjal, he's also interested in fluid mechanics, so he has told us that in order to have this flow over this tube bank, we need some kind of pressure difference, some kind of pump or fan to flow over this tube bank. So for that, he has told us that delta P would be equal to NL into NL is the number of tubes in the longitudinal direction, F is the friction factor, X is the correction factor, rho V max square upon 2. V max we have discussed. F and X, that is remains to be discussed. So if I show you the figure that how to calculate F and X for this. So they would be quite small. So I would make it a little bit zoom in to show it more clearly. But I would also show the calculations during the numerical. So don't worry about that. So there are two graphs. One is for the inline arrangement, you can see, and the other one is for the staggered arrangement. On the x-axis, we have got Reynolds number, and one thing you can see that is a logarithmic scale used on the x scale as well as on the y scale, because we need to have a very long range of data on the x-axis and y-axis, so that's why they have used this logarithmic scale. So if you see, there are one is the main figure in which there are three curves. So these are the curves for a parameter which is called PL. Okay. What is PL here? PL is SL upon D. SL is the longitudinal pitch divided by the diameter of the that tube. So if we know the PL and we know the Reynolds number for that particular flow, then we can determine the friction factor because we know PL. So and if let's suppose we have got 10,000 Reynolds number and PL is equal to like 1.25, then we take a vertical line from here and see that where it intersects with this PL line, and then we can see the value on the x-axis. It would give us F value. Okay. Now let me zoom a little bit more to show you the uh, another graph which is instead of this big graph. So let me do it maybe 600%. Now you can see this graph. We can on the x-axis we have got pt minus 1 divided by pl minus 1. What is pt? That is st upon d. What is pl? sl upon d. And if we know the transverse and longitudinal pitch, we can always get this x-axis value, ratio of these two. And then we have got Reynolds number. You can see 1000, then 10,000, and then 10 to power 6, 10 to power 5. They are not very clear. So if SL is equal to ST, then this quantity would be equal to 1, then there wouldn't be any correction factor needed. When SL is equal to let me repeat it. When SL is equal to ST, then it means that PT would be equal to PL, then it means that x-axis we would have 1 value, and 1 against 1 the correction factor would be equal to 1. So this correction factor is not needed. It is only needed when SL is different from ST. So don't worry about this. We are going to do this again in maybe 5 minutes time on the in the numerical problem. So the same thing it is shown here for the staggered one. So staggered one, that is a little bit more clear here. You can see the x calculation is that is a little bit more clear. So we can calculate this easily for the staggered arrangement. So I hope that it was clear. So it was first we get delta P. So once we get delta P, then if we want to know the pumping power required for that fan, blower or pump, whatever we are using to move that fluid across that tube bank, that can be determined like volume flow rate into delta P. That is the formula you must have come across during your fluid mechanics course, because the pumping power, that is always the flow rate into delta P. Delta P is the pressure difference between the first row and the last row. Okay? Because the pressure would drop from the first row to the last row because of the friction between that CD, which we discussed in the previous week lecture, that drag force discussion. Okay? So I think we can have a 5 minutes break, and then we can come back and do one numerical problem, which is this. So I would leave you with this numerical problem. You can read through the statement in the meanwhile, and let me take a breather, and you also, and then we can do the solution of this in detail. So we will meet in 5 minutes time. Thank you. Okay, ji. So I think we had a break for 5 minutes. So now we can go through a numerical problem that how to calculate Nusselt number and heat transfer rate for flow over tube bank. So the problem statement is, in an industrial facility, air is to be preheated before entering a furnace by the flow of geothermal water at 120 degrees centigrade flowing through the tubes of a tube bank. So it means that the geothermal water is flowing through these tubes, and air is coming which needs to be preheated before it can be combusted in. It can be used for combustion in furnace. So through the tubes, and that tubes, they are located in a duct. So it means that the air enters the duct at 20 degrees centigrade and atmospheric pressure with the mean velocity of 4.5 meter per second. So U infinity or V is 4.5 meter per second, and flowed over the tubes in the normal direction. So it is going this way, right? The outer diameter of the tubes is 1.5 centimeter, and the tubes are in it inline. So it means that we need to use the relations for the inline arrangement. With longitudinal and transverse pitches, ST is equal to SL. That it means that is the distance between two tubes in the flow direction, that is also 5 centimeter, and in the vertical direction, that is also 5 centimeter. There are 6 rows in the flow, so it means 1, 2, 3, 4, 5, 6, and there are 10 tubes in each row. It means that in the transverse direction we have got 10 tubes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many number of tubes in total? Anyone?
See.
60.
Okay, ji. So thank you very much for your input. So determine the rate of heat transfer per unit length, because these tubes are also going into the board, which is the which would have the length of the tube, because after that it would take a turn, then come back, and then at this it would take again the turn, and then it would continue in that way. So we need to determine the rate of heat transfer and the pressure drop across the tube bank. We need to know that how much, because the highest pressure of air would be here, then because of the friction, that pressure drag and friction drag, there would be a drag force which would make the pressure of that a little bit less when it comes away from this tube bank. So first of all, we need to determine Reynolds number in this case, but for the Reynolds number, we need to know the properties rho, U infinity, and other properties. So first of all, we determine those properties. Reynolds number from the table 0.7202. K of air, that is 0.02808, and then Prandtl number at the surface temperature of the tube, which is 120 degree here, that is 0.7073. This is determined at the TI, which is Prandtl number here 0.7202, and then 0.7073, that is determined at the surface temperature of the tube, which is 120 degrees centigrade here. Rho is 1.06 kilogram per meter cube. Mu value is given as 2.008 into 10 to the power minus 5. Rho I 1.204. Cp value, that is 1.007 kilojoules, so 1007 joule per kg Kelvin. G, any query? Okay, maybe not. So, in order to determine Reynolds number, we need to have the maximum velocity. So, because it is an inline arrangement, so for the inline arrangement, if we remember that we use this formula, Vmax is equal to St divided by St minus C into u infinity. So if we use that, so st upon st minus d into v infinity, so it comes greater than 4.5. It should be greater than that. So if that comes out to be less than 4.5, you have done something wrong in the either the calculation or the formula, right? So it should always come more than the approach velocity or the free stream velocity, which is 4.5. So now if we determine the Reynolds number, that comes out to be equal to 5091. So 5091. So if we go back to the table of Nusselt number here, it is inline arrangement and it is 5000. So 5000 mean that it lies in the third row, which is the range 1000 to 2 lakh. So 5000 is in this range. So Nusselt number relation is 0.27, Reynolds number d 0.63 into Prandtl number 0.36, and the next term. So 0.27, if you remember that C value. So if you see that 0.27 is here, 0.63, and then if we just plug in the values in the formula, we know the value of Prandtl number. Prandtl number at PRS is the Prandtl number at the 120 degree, which is surface temperature of the tube. So that comes out to be 52.2. But now, then again, if we go back to the statement, there are only 6 rows in the flow direction. So it means that we also need to incorporate the correction factor here. So if we go into the table and then see, there is no data for the when the rows are 6. So all we can do here, because we know the data at 5 and 7, so we can take the average. So 0.93 plus 0.96. So if we take the average, that would be 0.945. So f value is 0.945. So if we do that, 0.945, so Nusselt number would be equal to 0.945 into 52.2, so that comes out to be 49.3. Now we can calculate h value. So h would be equal to Nusselt number into k divided by d. K is k for the AS. So that is 0.02808 and diameter is 15 centimeter. So that is it is 15 centimeter, maybe 1.5 centimeter, I think, not 15. So it is 1.5 centimeters. So that's why it is 0.015 meter. So H value comes out to be 92.2. Now we need to use the formula for delta T. Q is equal to HAS delta T logarithmic. But for the delta T logarithmic, we need to know inlet temperature as well as the outlet temperature. Inlet temperature is given 20 degree, but we don't know the value of temperature TE. So for that, we use the formula which I had written on the whiteboard, as well as this formula which is on the slide as well. TE is equal to TS minus TI exponent minus AS H m dot Cp. Now, what is AS? AS is the surface area of the total number of tubes. So that would be equal to total number of tubes, which is n, which is in this case 60, pi into d into length. But because we are considering per unit length, so this would be equal to 1. And then m dot, which is the mass flow rate through the tube, that would be equal to rho into v infinity, rho I into v infinity into s nt into st into l. So it should be rho, not rho I. So nt value we know, in the transverse direction we are being given 10 number of tubes, st value is given 5 centimeter, and length again that would be equal to 1. So why NT? Because for the cross-sectional area in the y direction, we need height. So that's why we are using the number of tubes in the y direction, in the transverse direction, into the distance between two consecutive tubes. So that would give us the total height in the transverse direction. So it means that first of all we need to know the n value which is 60. बिल्कुल ठीक है. As I have told you, n pi dl, that is n is 60 pi into this, and then m dot, that is rho I v infinity n t s t l. So I think there should, in this formula it should be rho I. जो कि यहाँ पे मैंने लिखा है वो मेरे ख्याल में रो आई मिस कर गया हूँ. So please, I would make that correction here. It should be rho I here. So I would make that correction in the slide. So that rho I is written here. V infinity n t. Rho I is the density at the inlet. So that is comes out to be 2.709 kg per second. Now we have got m dot. Now we can determine TE from the formula. So if we put in the values, TS is 120, TI is 20, exponent AS we have calculated, m dot is given, CP is 1.007 kilojoule per kg, so it should be 1007 joule per kg centigrade. So this is the common mistake which many students make when they read the data. If it is in kilojoule, then you need to convert into joules. So then H value is 92.2. So if we do that, T comes out to be 29. So it means that physically, what does this 29 mean? That the flow uh, inlet temperature for the air was 20. So the at the outlet the temperature becomes 29. So it means that during these 6 rows the temperature only increased by 9 degrees. So if we want more increase, then we can do couple of things. Either we increase the number of rows or we decrease the mass flow rate of the air, then we can have that more increase as it flows through this tube bank. So their T comes out to be 29.9, and then we can calculate delta T logarithmic, that is Ts minus Te minus Ts minus Ti divided by log of the ratio Ts minus Te divided by Ts minus Ti. That comes out to be 95.4, right? So it comes out to be 95.4. So if we use this for the calculation of q dot, that comes out to be now we have got 24.9 kilowatt of heat transfer. So that was part 1, which was determining the heat transfer per unit length. The second part is to determine the if you go back to the statement, we need to determine the pressure drop. For the pressure drop, we need this formula: delta P is equal to NL into Fx rho V max squared upon 2. Now x value would be equal to 1. Why is that? Because St is equal to SL, then correction factor, that geometrical correction factor would be equal to 1, because the pitch in the transverse direction is equal to pitch in the longitudinal direction. So the only thing we don't know here, that is F, which is the friction factor. So for the friction factor, if you know that we need to use that graph. So I have written here that x value is equal to 1 for the square arrangement of the tube bank. For the F calculation, I have I would zoom it a little bit more. If you can see here, first of all, we need to know the Reynolds number. It was 5091. So if you see here that from here, 5000 would be between 4, I think maybe it was 5000. So 5000 would be somewhere here, and 5000 if we go in the vertical direction, and because no, for this case PL is equal to SL upon D, which is 3.33. Now you can see that we have got the curve for 3, but there is no curve for 3.33. So all we can do is that we can take this data from curve 3. So if we go draw a vertical line here, and then it intersects this PL line 3 here, and then if we draw a horizontal line here, then we can see that the value of friction factor comes out to be around I think 0.18 or 0.17 would be equally good. So here I have written 0.16, so it should be more than 0.15 and in between 0.2, so 0.16, 17, 18, they are equally good. So because it is a logarithmic scale, so it is very difficult to get the exact value, but it should be in that range as I have shown here, 0.1 and 0.2. So if we do that, so now we know the friction factor x is equal to 1, rho is given in the data we have seen from the table, Vmax we have calculated, so it means that the pressure drop is 21 Pascal only from pressure drop across this tube bank, right? So this was a numerical. Any query in this numerical, anything which you couldn't understand here? So if there is any query, you can ask. Otherwise, there are two, three practice problems. You can do it at your own time. Actually, 5 problems to get you familiarized with different kind of scenarios for the staggered arrangement. So I thought that I would give you these practice problems for the time being. So now we would have quiz number 4 in next week. So it would be from chapter number 7, which is the forced uh, external force convection, which started okay, and in the next lecture, which is actually tomorrow, we are going to start the second last chapter of this course, which is internal force convection, which is the flow inside ducts, pipes. So in that case, how do we calculate the heat transfer and H value? Okay, so for the quiz from chapter number 7, I don't know the exact chapter in the single, but I think it is chapter number 7. So in that we discuss 3 main topics: flow over flat plate, cylinder, and tube bank. So you can also include chapter number 6 and 7. Okay, so maybe from chapter number 6 I can ask a simple conceptual question, anything, and from chapter number 7 a small numerical would be there. So in next week's class we would have quiz number 4, which is from external force convection. So
सर
let me
वेडनेसडे क्लास में होगा
जी दोबारा बताइए
वेडनेसडे
जी
वाली
वेडनेसडे वाली
क्लास में
क्लास में
होगा
जी
कि ट्यूसडे वाली में
वेडनेसडे वाली क्लास में ले लेंगे जो 1 वीक वाली होती है, जो 1 आवर वाली होती है. वी आर डूइंग द सेम थिंग फॉर दिस कोर्स, so I think we can keep that tradition. So we can have the quiz in the Wednesday class, which is actually 1 hour class
सर
next week. ठीक है.